Section 1 Introduction. In this introduction, we discuss the challenges and limitations of large language models, LLMs, such as GPT-3, which require vast computational resources for training, fine-tuning, and evaluation. Many researchers are working on creating smaller, more efficient LLMs that can operate on consumer-grade hardware. However, a definitive solution for creating resource-efficient neural networks is still elusive. One promising approach is the use of sparse mixtures of experts, MoEs, which only compute a subset of their activations at each step, reducing computation and memory costs. However, MoEs are not widely adopted due to some common misconceptions. They are difficult to train, they are not as effective as their dense counterparts with the same number of parameters, and they are only suitable for extremely large models. We challenge these misconceptions and propose new perspectives on MoEs. We present MoEs within a unified framework of methods that approximate two-layer feedforward networks, which includes product key memories, PKMs, and top-K sparsification. This view allows us to compare MoEs with PKMs and provides insights on design choices for improving these methods. Our MoE transformer variant outperforms our improved PKMs, and performs as well as or even outperforms the dense baseline, while using a fraction of its compute for both training and inference. We compare our MoEs with dense baselines with the same number of total trainable parameters, which is crucial for proper evaluation in language modeling. We conduct experiments on the standard Wikitext 103 and NWIC 8 datasets. We demonstrate that MoEs are not limited to extremely large LLMs, but useful as a generic approach for resource-efficient neural networks at any scale. We also release a CUDA kernel for our MoE layers, which allows for achieving faster wall clock time and large memory reduction compared to the dense model. Transformers have two main building blocks, the self-attention layer, and the two-layer feedforward, i.e., multi-layer perceptron, MLP, block. While the acceleration and memory reduction of the self-attention is well explored, resource-efficient MLP blocks are still underexplored. This is our main focus, as the proportion of the total parameter counts, compute and memory requirements due to MLP blocks in transformers is increasing in ever-growing LLMs. Each transformer MLP block consists of one up projection layer with a weight matrix W1 of size D_FF by D_model, where typically D_FF is 4 times D_model, and one down projection layer with parameters W2 of size D_model by D_FF that projects it back to the original size. Non-linearity, typically ReLU, is applied between these two layers. That is, an input X of size D_model is transformed to an output Y of size D_model as follows. U equals ReLU, W1X, and Y equals W2U, where U is of size D_FF. Alternatively, this layer can be viewed as a key-value memory accessed by attention, where keys and values are rows and columns of weight matrices W1 and W2. Then, the output is computed as attention. Y equals sum of V_I asterisk ReLU, K_I caret T asterisk X, for I from 1 to D_FF, where alpha_I equals ReLU, K_I caret T asterisk X, are the attention weights. Note that alpha_I equals U, I, where U, I, denotes the ith component of U in EQ. Unlike the standard self-attention, the MLP block uses a ReLU activation function, instead of the softmax, without scaling. It has been observed that, in practice, only a few of the factors K_I caret T asterisk X are positive, making the first layer's output, i.e., U, sparse. In a transformer with D_model equals 256 and D_FF equals 1024, 10% of the channels account for 90% of the total activation mass. We confirm this trend in our own preliminary study. This suggests that the MLP block can be approximated without a significant performance loss. Section Summary. In this section, the authors introduce the concept of sparse mixture of experts, MoEs, as a resource-efficient approach for neural networks. They challenge common beliefs about MoEs being difficult to train, not competitive with dense counterparts, and only suitable for extremely large models. The authors propose a unified framework that combines MoEs with product key memories, PKMs, and top-K sparsification, resulting in a MoE transformer variant that outperforms improved PKMs and performs as well as or even better than dense baselines, while using less compute for training and inference. They also release a CUDA kernel for their MO layers, which achieves faster wall clock time and large memory reduction compared to the dense model. Section 3. Approximating two-layer MLPs. In this section, we'll discuss a unified approach to approximating two-layer multi-layer perceptrons, MLPs, which includes methods like mixtures of experts, MoEs, and product key memories, PKMs. Let's start with some basics. Suppose we have an approximation of a vector y, denoted as y hat, in a model space. We can represent each element of y as a product of a scalar alpha and a vector versus the main idea is to approximate the sum of all elements of y by only keeping a subset of the key value pairs. This approximation works on the assumption that a good approximation of y is one that minimizes the Euclidean distance between y and y hat. This distance can be expressed as the sum of the products of alpha and v for all elements not in the subset. We can minimize this distance by ensuring that each term in the sum, represented as c, is small. If we assume that all vectors versus have the same norm, the quality of the approximation depends on the attention weights, alpha. We refer to alpha as the contribution of each key value pair. The general idea of all methods discussed here is to keep the top k pairs with the highest contribution and ignore the rest. The challenge is to find the best way to select these top k pairs. We'll discuss three variants: top k activation, product key memories, PKMs, and mixture of experts, MoEs. The simplest implementation of this approximation is the top k activation function. However, this method only saves less than half of the total computation. To further reduce computation, we need to introduce some approximation to the activation function, as done in PKMs and MoEs. Product key memories, PKMs, involve replacing the weight matrix in the activation function with two smaller matrices. The input vector is split into two halves, and the matrix multiplication is performed on these smaller vectors. The resulting vectors are then combined in all possible ways, similar to the outer product but using addition instead of multiplication. In addition to applying top k at the output, top k can also be used to speed up the operation above. By applying top k to the smaller vectors before combining them, only the top k squared components need to be calculated. These are guaranteed to contain the top k components of the full vector. In the original formulation, PKMs use a softmax activation function, inspired by self-attention. However, we'll show how a non-competing activation function, such as ReLU, is a better choice. Section Summary. In this section, the authors present a unified view on approximating two-layer MLPs by only keeping a subset of key value pairs. The goal is to minimize the Euclidean distance between the approximation and the original output by selecting the k pairs with the highest contribution. Three variants of this approach are discussed: top k activation, product key memories, PKMs, and mixture of experts, MoEs. The authors also introduce the implementation of PKMs, which involve replacing a matrix in the MLP with two smaller matrices and using Cartesian products to calculate the output. Section 3.3 Mixture of experts, MO. Let's delve into the concept of mixture of experts, MO. Imagine we have a set of key value pairs, denoted as k_i, v_i. We divide these pairs into n_e groups, each containing g pairs. The total number of pairs, d_ff, is equal to the product of n_e and g. We have two weight matrices, w_1 and w_2, which are divided into smaller matrices, w_1_e and w_2_e, for each group. These smaller matrices are derived from the original weight matrices by selecting specific rows and columns. The output of this process is calculated using a formula that involves the application of the ReLU function to the product of the input and the first weight matrix, w_1_e. This result is then multiplied by the second weight matrix, w_2_e, and a scoring vector, s_e. The scoring vector is computed by a function called cell, which typically uses the softmax function. The scoring vector is then used to select a subset of indices, e_x, from the set 1, n_e. This selection is done using a top k operation, which picks the k highest values. In some cases, the selected scores are renormalized so that their sum equals 1. The efficiency of MoEs comes from the fact that the number of groups, n_e, is much smaller than the total number of pairs, d_ff. Moreover, the product of the group size, g, and the number of selected indices, k, is also much smaller than d_ff. This makes the computation performed by the experts less costly than a dense multi-layer perceptron, MLP. The main challenge with MoEs is to design a selection function, cell, that assigns high scores to only a few experts without compromising performance. This is crucial to avoid a problem known as expert collapsing, where only a few experts are used and the rest are ignored. To prevent this, we usually apply some form of regularization to the selection score, encouraging a more even distribution of experts across all tokens. In the next sections, we will review various MoE variants and present our improved version. Section Summary. In the mixture of experts, MoE, approach, the weight matrices are partitioned into smaller matrices for each expert group, allowing for efficient computation. The output is computed by summing the contributions of each expert group, weighted by the expert scoring function. The challenge is to learn a selection mechanism that assigns high scores to a few experts while avoiding expert collapsing, where only a few experts are used. Regularization techniques are typically applied to encourage uniform routing of experts across the batch of tokens. Section 4. Existing MoE variants. Let's delve into the existing variations of mixtures of experts, MoEs. We'll focus on the most popular and representative ones, excluding those that use reinforcement learning for expert routing. We'll examine their expert selection function, regularization method, and key characteristics before we introduce our improved version. Firstly, we have the sparsely gated mixtures of experts. They revisited MoEs with the top K operation, which allows for a reduction in resource demands. Their method is similar to the one we've previously described, but they use a noisy gating function. This function is a softmax operation applied to the input vector multiplied by a weight matrix, plus a Gaussian noise term. This noise term is element-wise and independent for each channel. They also use an auxiliary regularization term for load balancing, which is the coefficient of variation of the sum of the norms of the selection function applied to all tokens in the batch. The key characteristic of this method is that the scores are normalized after the top K operation, which is equivalent to applying top K before the softmax. Next, we have the switch transformer. They integrated the MoE above into the transformer to create their switch transformer. They claim that top 1 routing is enough. Their selection function is simply a softmax operation applied to the input vector multiplied by a weight matrix. They propose a hard load balancing between experts that run on different hardware accelerators. They limit the number of tokens that can be routed to an expert based on a capacity factor, which defines how many times more tokens can be processed by one expert compared to the ideal case of uniform routing. For regularization, they calculate the fraction of the tokens processed by each expert and the average selection probability for each expert. They also use dropout with a high drop rate in the experts. They propose to initialize the experts with a certain value. The key characteristic of this method is that top 1 is applied after the softmax without renormalization. Then, we have the base layers and S-space. Inspired by the routing strategy and the hard capacity factor of the switch transformer, they propose base layers. They use top 1 routing and a sigmoid activation in the selection function. They solve a linear assignment problem to find the index of the expert to which each input is routed. This guarantees uniform assignment of experts, which is efficient for multi-accelerator training. However, at inference time, no such balancing is possible because not all tokens of the sequence are available at each step. They show that, while during training, the routing is enforced to be completely uniform, during the test time, the distribution looks exponential. The algorithm for solving the linear assignment problem is difficult to implement efficiently on modern accelerators. They propose to use the Synchrn algorithm instead, to approximate the solution to this problem. They report that this works well, while being simpler to implement. The key characteristic of this method is that during training, Synchrn iterations are used on scores to obtain a balanced assignment. The sigmoid activation is always applied to compute the weighting score. In summary, all load balancing methods above are rather complex. We propose a simpler but effective approach for MoEs in the following section. Section Summary. In this section, the authors review existing variations of MoEs, such as sparsely gated mixtures of experts and switch transformer, highlighting their expert selection functions and regularization methods. They also introduce base layers, inspired by the routing strategy of switch transformer, which use top-1 routing and a sigmoid activation function. The authors propose a simpler and effective approach for MoEs in the following section. Section 5. Improving mixture of experts. In this section, we'll discuss our enhanced version of the mixture of experts MoE model, which we've named Sigma MoE. We've conducted comprehensive studies to understand the impact of our design choices, which we'll discuss in detail. Firstly, we've made changes to the expert selection function in our MoE model. Unlike the base model, we use the top K operation. We've also chosen to use the sigmoid activation function instead of the softmax function, which is used in the switch transformer and sparsely gated mixtures of experts models. This decision is based on the idea that MoEs can be seen as a rough equivalent to two-layer multi-layer perceptrons, MLPs. The softmax function can create competition between experts, which isn't present in a regular two-layer MLP. This suggests that we don't need competition between terms in the MoE to achieve sparsity. It's also known that using softmax as a regular activation can negatively impact the trainability of standard MLPs. When combined with top K, softmax can lead to expert collapsing, where if one expert's selection score increases, the others automatically decrease. For these reasons, we've chosen to use the sigmoid function instead of softmax, and our experiments confirm this was a good choice. We've also considered how to combine MoEs with top K activation for further acceleration. We calculate the activation for the selected experts and perform an additional top K operation to keep the highest units and set the rest to 0. However, we'll explore this further in future work. Next, we've made changes to the initialization of our Sigma MoE model. Typically, experts are assumed to be independent, and the standard deviation of the initialization of the weights is calculated based on G instead of D_FF. Our experiments show that this is not the best approach. Instead, we initialize all weight matrices identically to the pre-layer norm dense baselines, without considering the smaller size of the individual experts. We also take special care when initializing the weights of the selection function to ensure that the rows of the weight matrix have the same norm. This prevents experts with smaller norms from being overlooked, as their selection score would be low even if the selector fully aligns with the input. Finally, we've made changes to the regularization of our Sigma MoE model. Existing regularization methods for load balancing are complex. In contrast, we propose to simply maximize the entropy of the selection distribution calculated across the entire batch. This encourages equal expert usage within the batch and prevents unnecessary overconfidence in selecting individual experts. We also propose randomly dropping complete experts during training, which we refer to as expert dropout. Unlike standard dropout on the activation level, we don't apply rescaling. This prevents the dropped experts from being selected while not affecting the others. When an expert dropout removes a popular expert, it forces the less popular ones to take over, increasing their chance of being trained and improved. Our experiments show that our regularization method and expert dropout are both effective despite their simplicity. Section Summary. The authors propose an improved variant of the mixture of experts MoE model called Sigma MoE. They use a sigmoid activation function instead of softmax to avoid competition between experts and improve trainability. They also introduce a simple regularization method to encourage equal expert usage within the batch and prevent overconfidence in selecting individual experts. Section 6. Experiments. In this section, we'll discuss the experiments we conducted. We based our experimental setup on the Transformer XL model, but made a few changes. We used pre-layer normalization and reduced the number of training steps to 100,000 to save on computational resources. To ensure a fair comparison between our baseline model and the mixture of experts MoEs model, we adjusted the hyperparameters of the baseline model. Our MoE model requires dimensions that are multiples of 4, so we rounded up the original sizes to the nearest suitable number. For example, we increased the model size of our 47 million parameter Wikitext 103 model from 410 to 412. Since MoEs need additional parameters for expert selection, we increased the size of the baseline model to match the number of parameters. We used the sentence piece tokenizer for Wikitext 103 instead of word-level vocabulary to avoid the need for additional tricks to manage the large vocabulary size. We tested two different model sizes for Wikitext 103, a smaller one with 47 million parameters and a larger one with 262 million parameters. We used all the methods we considered in every MLP block of the model, which is not a common practice. Usually, MO or other approximation methods are used only in certain layers. However, our goal was to find a method that could speed up all layers across the entire model. We first evaluated the top K method. We found that not only did top K preserve the performance of transformers in the MLP blocks, it even improved performance. We believe these improvements are due to a reduction in feature interference. However, we can't just reduce K arbitrarily. There needs to be a balance between the denoising effect and the network's capacity. We found that the optimal value for K is either 128 or 512. Next, we evaluated the product key memory, PKM, method. We found that using a non-competitive activation like ReLU instead of the softmax used in the original PKM improved performance. However, even the best PKM models didn't perform as well as the dense baselines, indicating a fundamental limitation of PKMs. Finally, we evaluated our Sigma MO models on NWIC 8 and Wikitext 103, as well as two additional datasets, C4 and a newly proposed dataset. Our Sigma MO models matched the performance of their parameter equal dense baselines, while significantly reducing memory and compute requirements. These models used K equals 4 for 16 or 32 experts, which is a moderate level of sparsity but still offers significant compute reduction. However, there is a limit to how much sparsity can be used while still maintaining good performance. We found that experts with a group size of less than 128 generally decreased performance. We also found that the minimum number of simultaneously active channels needed to be above a certain threshold, usually around 256 to 512. Under these constraints, we found that the performance of the dense baselines could be matched using 25% of the required computations in memory for our small models, and 12.5% sparsity for the big one. Section Summary. The experiments in this section focus on evaluating different methods, top K, product key memory, PKM, and mixture of experts, MO. The top K method improves the performance of transformers by reducing feature interference, with an optimal value of K equals 128 or K equals 512. The PKM models with ReLU activation perform closer to the dense baselines, but still underperform them. On the other hand, the Sigma MO models achieve comparable performance to the dense baselines while significantly reducing memory and compute requirements, with a moderate level of sparsity, K equals 4, offering substantial reduction in compute. Section. Increasing N_E and impact of sparsity. We found that our Sigma MOs can be adjusted to achieve the desired performance with fewer resources. To further test this, we increased the number of experts, N_E, from 16 to 128, while keeping the number of selected experts, K, at 4. This increased the number of parameters to 238 million, but the speed and memory requirements remained similar to the original model. However, the test perplexity was 10.37, which is worse than the 9.46 of the 262 million parameter dense model. This suggests that even when the number of parameters is the same, other factors can still limit performance. For example, the dimension of the model, D_text model, was much smaller in this case, 412 versus 1024. We also created another dense baseline model with the same hyperparameters as the 47 million parameter model, except for the feed-forward network dimension, D_text FF, which we set to 16,480 to match the number of parameters of the 128 expert MO. This model had a perplexity of 10.03, showing that there's still a significant gap between the performance of the scaled-up MO and its dense counterpart, 10.37 versus 10.03. This highlights the importance of controlling MO sparsity to maintain its performance against the dense baseline. We compared our Sigma MO to other MO variants, such as the switch transformer and S-base. Unlike the original models, our implementation doesn't enforce hard balancing based on capacity factor. We also compared sigma Mo to the most important baselines on the C4 dataset. As the switch transformer and S-base only select one expert, k equals 1, we increased the expert size by a factor of 4, from 128 to 512 in our models, and decreased the number of experts by the same factor for a fair comparison in terms of parameter count. Neither of these models uses our proposed expert dropout. Our sigma Mo outperformed both the switch transformer and S-base, even when considering all these factors. We also conducted ablation studies to examine the impact of individual design choices. We found that using standard dropout instead of expert dropout led to performance degradation in most cases, except for the model with 128 experts. The softmax-based selection functions consistently performed worse than our sigmoid one. The same was true for the standard initialization. Our method was better. Interestingly, removing all regularization methods degraded performance but didn't cause catastrophic collapse even with 128 experts. We also found that a high k equals 4 works best within a certain range. A common issue with MoEs is expert collapse, where only a few experts are used while others are ignored or underused. We analyzed various models, including ours, to see if they were affected by this issue. We calculated the proportion of the expert selection weights assigned to each expert on the entire validation set of Wikitext 103. Models with poor performance, such as the switch transformer and a variant of sigma Mo with a softmax and renormalization, suffered from the expert collapse problem. However, our entropy regularized models with expert dropout, especially sigma Mo, were able to match the expert usage balancing of S-base without using the synchrone activation function. We don't consider uniform expert activation to be optimal, as we expect experts to specialize and their usage frequency to depend on the occurrence of the tasks they are performing.